So I'll be talking about the dynamics of gradient flow in overparameterized linear models. And this is joint work with Guy Fransab, Benjamin Heffley, and René Vidal. So as you might all know, in deep learning, we're typically working with neural networks that are highly overparameterized, meaning that they have many more learning weights compared to the training examples. This leads to problems that are highly underdetermined with many possible solutions that all fit the data perfectly. And in practice, we use variance of gradient descent to find one of these solutions. So although this works pretty well in practice, there are still a lot of mysteries regarding the behavior of these gradient descent algorithms. And mainly, we were wondering what the effect of overparameterization is on the learning dynamics. So in recent years, there has been an extensive body of work trying to answer this question. Some have suggested that perhaps overparameterization promotes generalization, which is what is typically referred to as implicit bias or implicit regularization, while others suggest that perhaps overparameterization accelerates convergence, and that is what is referred to as implicit acceleration. The caveat, though, is that most of the existing analysis makes strong assumptions on the initialization. Namely, they require it to be either spectral, vanishingly small, or balanced. And I'll explain what those types of initializations are in the next slides. So our goal is to also analyze the dynamics of gradient flow, the continuous version of gradient descent, in two-layer linear networks, but under more general initializations. And we will show that, first of all, overparameterization results in conservation laws that constrain the dynamics to follow certain trajectories. And more importantly, because of these conservation laws, we get a convergence rate that depends on the initialization. So we will get this imbalanced quantity that I will define in future slides, as well as capturing the eigenspectrum of the data here. So to start, I will start with a very simple warm-up example, which is just considering this objective function, 1/2 of y minus x squared, that we're trying to minimize using gradient flow. So this is not at all interesting from a practical standpoint, but it will help us illustrate the effect of overparameterization. So we assume that y is a known scalar that we're trying to learn, and we're running gradient flow on x. So the dynamics are very simple. They're just captured by this differential equation here, x dot is equal to y minus x. We can solve it in closed form, and the convergence rate is simply e to the minus t. So what does it mean for us to overparameterize this problem? Well, it means to replace x with a product of two parameters, u and v. So it's almost as if we go from depth 1 to depth 2, and when we run gradient flow on u and v, we get these slightly more complicated dynamics. So we have two differential equations on u and v, and the question is, what is the solution to this problem, and more importantly, what is the convergence rate? So before we get into the solution, it's very important to first notice that this problem actually has a scaling symmetry, meaning that if we take any solution or any parameters u and v and multiply u by some non-zero scalar alpha and divide v by the same non-zero scalar, then we get another solution that corresponds to the same loss function. And for those who come from a physics background, we know that symmetries in general are related to conservation laws. So here the quantity that is conserved ends up being u squared minus v squared. And it is equal to its value at initialization, which we denote by lambda 0. We will refer to this quantity as the imbalance because it captures the imbalance between the weights. And so in terms of the trajectory, what this means is that if we look here at the plot, so we have u on the x-axis and v on the v-axis, and this red curve represents the critical points for our problem. So different values of lambda 0 of the imbalance at initialization will give us different hyperbolic trajectories. So for example, if we start here with an imbalance of 10, we will get this trajectory, and that'll tell us which point we'll converge to on the red curve. We do have this very special trajectory that is just a straight line, which corresponds to the balanced case. So that's when the imbalance is simply 0. So now the question that we're really interested in is how does the product x, which is u times v, behave during gradient flow over u and v? Because that's what we really want to compare to the non-overparameterized case. And it turns out that that's captured by this nonlinear differential equation now. So it's x dot is equal to y minus x times the square root of the first term is simply the imbalance at initialization that we saw in the previous slide. So that already relates it to the conservation laws, plus 4x squared. Luckily here we can solve it in closed form, which is this pretty complicated formula. And what's really interesting is that the rate of convergence ends up being a function of both the imbalance at initialization and the data, which is simply captured by the scalar y. So just to summarize what we've seen so far in this scalar case, so we started with this objective, just 1/2 of y minus x squared. We tried to overparameterize it. We saw how we went from this simple linear ODE to something that is nonlinear and that depends on the conservation law. The solution is obviously also going to be different. And for the rate of convergence, we went from something that is e to the minus t that does not capture anything about the initialization or the data to something that actually depends on both quantities. So now obviously we're not just interested in analyzing the scalar case, we want to see what happens for neural networks. And so the setup is that we're considering a 2-layer linear network with a squared loss. So the xi's and yi's are training data, and we use U and V, the weight matrices for this network. Both of them have a number of columns, k, that is larger than the minimum between the input and output dimensions. So that ensures that we're not in a case where it's a low-rank factorization, basically. And we make this assumption that the data is whitened, which is a common assumption, meaning that the input correlation matrix is equal to the identity. And this allows us to show that the problem is actually equivalent to a matrix factorization. So it's almost as if we're trying to factorize the input-output correlation matrix. And just to simplify the notation, we'll simply be replacing that with the matrix Y. So from now on, we'll just be factorizing the matrix Y. So again, we're looking at the dynamics of gradient flow applied on, first, a 1-layer model, which is very trivial. So it's just looking at the minimum of 1/2 of the squared Frobenius norm of y minus x. And we overparameterize that in 2 different ways. So the first one is a symmetric factorization, which corresponds to a 2-layer model with tied weights. And the second one is an asymmetric factorization. So in that case, we don't make any constraints on the weights. So this is very similar to the scalar analysis. We get sort of the same equation for gradient flow, so x dot is equal to y minus x. The solution also looks pretty much the same. And again, we get that convergence rate of e to the minus t. So first, we tried the symmetric factorization. So now we're running gradient flow on u, which gives us these dynamics for u. And once again, we're more interested in the product because that's what we want to compare to the non-overparameterized case. So we try to look at the dynamics of UU transpose. So they're given here by this quadratic equation, and what's really interesting about it is that it's actually a Riccati equation. And Riccati equations have been extensively studied in the control theory literature, so we can leverage some of those results to understand the dynamics here. One last thing to note is that because in this problem we have a symmetric factorization, the solution cannot be it has to be positive semi-definite. So x can only converge to something that ideally is going to be the projection of y onto the positive semi-definite cone. So using the fact that we have that Riccati equation that describes the dynamics, we actually know how to solve that in closed form, so that gives us a solution for x that's given here. And from this, we can try to analyze and get a convergence rate. So first, we'll start with the case where we assume a spectral initialization. So what this means is that our initialization has the same eigenvectors as the data matrix. So if this is the eigen decomposition of our data matrix Y, then the initialization has the same eigenvectors in its eigen decomposition. And when that happens, we have two interesting things. The first one is that the eigenvectors remain constant throughout the trajectory, so only the eigenvalues are changing. And so the dynamics actually reduce to scalar dynamics just on the eigenvalues. We can solve those dynamics in closed form, so we get a solution for each eigenvalue of the matrix X, so those are the sigma I of T. And what's interesting here is that each eigenvalue will converge at a rate that is e to the minus 4t times the absolute value of the corresponding eigenvalue of the data matrix Y. So basically, the larger the eigenvalue, the faster we learn it. And the global rate of convergence has to be determined by the smallest one. So it's obviously going to be e to the minus 4t times the smallest eigenvalue of the matrix Y. Why is this not moving? Oops. So now if we don't assume a spectral initialization, can we get a convergence rate? Well, the answer is actually yes. So for almost any initialization that is positive semi-definite, we get the same convergence rate of e to the minus 4t times the smallest eigenvalue of Y. And here, almost any initialization, obviously there are certain pathological cases where we cannot converge to the solution, but with almost any initialization, we can get this convergence rate. So now we move on to the asymmetric factorization. So again, we're just generalizing the scalar case where so instead of working with just scalars, we have the products of matrices. So the gradient flow dynamics look pretty much the same. In terms of the conservation law, so we had u squared minus v squared that was conserved before. And now it ends up being the u transpose u minus v transpose v that is conserved. So once again, we look at the case where we have a spectral initialization, meaning that our initialization has the same eigenvectors as the data matrix. And once again, in that case, the eigenvectors remain constant throughout the trajectory, and we are only learning the singular values. So we get scalar dynamics for each singular value, and here the solution, if you recall, is the same as the solution that we saw for the scalar case. So we can conclude from that for each singular value of x, we get a convergence rate of e to the minus t times this square root of, so the first term is going to be the ith eigenvalue of the imbalance matrix, and the second term is simply the ith singular value of the data matrix Y. And we have here this plot that shows this basically. So we're trying to factorize a 5 by 5 matrix using both the asymmetric factorization or just the trivial one-layer case. And we see that when the imbalance is small, so that's what we have on the left plot, then the largest eigenvalues are learned much faster than the smallest ones. And as we move to the right, so as we increase the imbalance, we start to see that even the small eigenvalues are learned faster. So now we can assume a non-spectral initialization. And recall that first the imbalance matrix is this u transpose u minus v transpose v. And so here, in terms of the rate of convergence, we can show that if the imbalance is 0, so that's the balanced case, then the rate of convergence will only depend on the data matrix. So that's going to be e to the minus 2t times the sigma min, so the smallest singular value of y. We can also look at a case where it's not balanced. So in that case, we assume that the imbalance is homogeneous, meaning that it's simply a scaled identity. So that's going to capture the degree of imbalance between the weights. And the reason why we make this assumption is that the dynamics once again reduce to a Riccati equation. And the convergence rate ends up being e to the minus t times the square root of, so once again, the first term, the lambda 0, captures the imbalance at initialization, plus the second term that captures the smallest singular value of the data matrix. So to conclude, the goal of our work was to provide a precise characterization of the solutions of gradient flow for overparameterized two-layer models. The main takeaways are that conservation laws constrain the system to follow particular trajectories, and that they have really important role in terms of the convergence rate. So we saw that the convergence rate will, in all of these cases, depend on the imbalance at initialization due to this conservation law, and on the singular values of the data matrix. And more importantly, we did not make any assumptions of balanced or vanishingly small or even spectral initializations. Thank you.